welcome everybody. Seminar 2, and right, over to you, Barry.
Good afternoon, guys and girls. Thanks for joining us for the second of the seminars on this MODSIM methodology we're going to be talking through. Again, thanks for joining. If you've seen the first one or the other day, again, the recording will be on the website. So by all means, if you've not seen it, be able to download it and go through the information on there. Obviously, what you can see there, I'm Barry Chatham. I've been with TECHNIA for the last couple of months now. So again, big learning curve for me. I'm going to learn a lot more on the platform and being part of the team, the way they do stuff here at TECHNIA. I've been an engineer for the last 20 years and with SOLIDWORKS for the last 10 to 15. So again, a lot of the methodology with the MODSIM, I understand firsthand. Test early is part of the design process and kind of get your models right, ready for manufacture. There's nothing worse than being, you go to manufacture and it becomes a very expensive thing to either miss the market or kind of incur significant costs for things failing when you're in there. So yeah, like I say, make sure you watch the first one. I hope it's going to be kind of beneficial for you all. There's some really sort of nice little topics in here, so hopefully you'll get a fair bit from here.
So, and I'm Andrew Steele. Very similar background to Barry. Product design and designing for manufacture for the good 10-15 years using CAD. And this seminar touches on a point that really hit home for me when I really started thinking about simulation and talking to one of our experts here. And they talked about understanding more than just the product performance and actually looking at manufacture, but we'll touch on that as we go forward. But it just reinforces that whole MODSIM theory philosophy that we discussed in that first video, and we'll discuss again in the third, and it's very, very obvious where it's being implemented through this presentation. So yeah, we'll move on.
Yeah, so like I say, the first one we went through was the large machinery, the resonant thing. So running a linear static analysis on the boom arm, applying a new bit of equipment to that boom arm and seeing what forces are being applied to that to make sure that it's not going to fatigue and fail. It's going to, we still become the market leader by doing the tests early, making sure that the product's right for market first time, and it hits the ground running. The second one, this one now, we're going to be looking at this, the railway train dolly, in particular the bushing for the suspension on there, looking at kind of non-linear analysis on that one and seeing how that performs. And the third one, which is going to be next week, looking at this high pressure water jet for cutting steel. So by all means, make sure you register for that one. Come along. Hopefully they'll all be beneficial and make sense, this whole MODSIM approach. Because like I said, Andrew just said, is very close to both our hearts. We've been there, lived it, felt the pain that you guys go through on a daily basis. So hopefully this approach you'll all agree is well, I think the outcome is very beneficial based upon the theory that we talked through in here. Is that right, Andy?
It is, absolutely. And from every angle, be that the engineer who's in the design office trying to come up with a new idea but scared of putting it forward because he thinks it might fail, to the design manager having the confidence to sign off on a revision or a change, or the MD who is doing the feasibility study of a new product. I really believe that MODSIM should just be used everywhere within the design engineering process.
Or a marketeer, Andy. You know what it's like with marketing, people saying, I've got an idea for a product. Can you just get that to market quickly?
Yeah. And even in marketing, they use something called A/B testing. They start putting things out, but they do 2 versions and see which works better. So rather than putting all their eggs in one basket, they're doing 2 different ideas at once, and once they know which one's going to be better, they go forward with that and put the investment into that. The MODSIM is being used all over industry, and it's just, we need to be doing it more in the engineering world, in my opinion. Well, I'm sure we both agree there, to be fair, isn't it? It's not like I'm saying something that you don't know already. So what we're going to be using, we're going to be using the 3D Experience platform. for specifically the SolidWorks side of that. And as we covered in the last seminar, it's just an integrated design-centric cloud-based solution for PLM, product lifecycle management. Everything from that initial concept or thought through to revision, change management. It's scalable it's in all industries. So if you're working in the medical devices, if you're in industrial equipment, if you're in the pharmaceuticals, all of those different industries have got a solution within the platform. So yeah, if you're looking to try and build that collaboration within your product development, get in touch and we'll be able to find a solution that works for you.
Mm-hmm.
So similar to last week, the last seminar, we're going to be working with SolidWorks as our CAD package, and we're going to be integrating that with SIMULIA on the platform to do our simulations. SIMULIA obviously using the Abacus solvers, highly regarded and well known within the industry. When we say SIMULIA, you could automatically understand that we're also talking about Abacus. And although we're talking very much about SolidWorks being the CAD platform here, CATIA, the bigger brother of SolidWorks, is interchangeable. So if you're used to living in the CATIA world, then just swap the word CATIA for every time we say SolidWorks, and you're going to be able to work through exactly the same process as we do here.
Right, guys, so we've got this assembly here of a dolly from a railway. Could be the actual, well, it could be a trail, I don't really know. But they had, what we were interested in is the bushing to make sure that the load, kind of the movement's not going to fail, and they'll run the checks on that one. Is that right, Andy?
Yeah, it's yeah, and so the bushing that Barry mentions there looks like this. A hub in through the middle with a plasticized rubber between it and the ring around the outside to connect it to the machine that it's within. Now we have been modeling this in the SolidWorks platform, but we need to understand with this more than just how it's going to perform in the field. We want to consider how it's actually being manufactured and what influence that manufacturing process has on the performance of the product. So how is this thing manufactured? It's a multi-step process. We've got a hub made out of steel, which we wrap in rubber, maybe injection molding, and then we wrap that with the outer ring. That's heated to 430 degrees Kelvin to vulcanize the rubber.
Mm-hmm.
And then it's cooled back down to 300 degrees Kelvin. Now, as this cooling happens, residual stress can build up in that rubber. Now we don't want that. It could affect the performance of the product and cause it to fail. And we want to understand what's going on there. So as I say, the thermal coefficients of that and between the rubber and the steel, it induces some residual stress. So the process that we're going to go through to remove that is by applying a compression load of 2 millimeters radially around that rubber. Now, as this is squeezed, it's going to normalize all of it and release all of that residual stress, and then it's going to be released, and it's going to spring back that little bit. So this is stuff that we just wouldn't know if we were just diving straight in and assuming what size things were going to be. We want to understand whether it's, if we squeeze it 2 millimeters, is it going to spring back 1? Is it going to spring back 0.25? And we can only figure that out. We can't, or we can guess. And there may be, like in the video we talk about, there may be an old guy in the corner who goes, yeah, well, if you squeeze that 2 mil, it's going to pop back 1. But we want to know that without having to go and call him. So the performance target of this bushing It's going to be fixed at each end of the hub. And then it's going to have a vertical load applied to it. And also it's going to get lateral loads applied to it. So we want to make sure that the rubber bushing allows movement as much as we can, but within our performance KPIs, so that it reduces the vibration that is going through to whatever it's attached to. But we don't want it to be so loose that it breaks, or we also don't want it so hard that it ruins the machine as well. So there's a bit of a balancing act that we've got to go on here, and it might mean that we need to do a few exploratory design changes to make sure that we get that right.
But again, following the MODSIM approach, Andy, test early, get it right, test it again, yeah.
Exactly. Yeah. And we're going to touch on how we do that in this.
Mm-hmm.
Let's get this on this in. So what's the first step? Like last time, we've started with this being modeled in SolidWorks, and it's been modeled on the desktop, and we need to push that up to the cloud, so it's then accessible to the team, to the simulation engineer. So we'll quickly run through that. There we go. So like we did with the resume, we've got the geometry open inside SolidWorks, and we're going to save it up to the platform.
Going into the right division, yeah.
Yeah, make sure it's converted. I think this is done automatically now, but so there we go. Got green ticks all the way down the status, so we know that it's been saved up there.
Mm-hmm.
Is that playing the same video again?
Yeah, it is, yeah.
Yeah, it is. Oops. 15. There we go. So what we've got there is a really easy connection between the desktop version of SolidWorks and SIMULIA through the connector. Now, we've got a whole host of licensing, everything that could suit everything from a small short-term project up to multi-year projects. So yeah, and we can help you figure out what it is that you need there. And like I mentioned earlier, this is all running Abacus solvers. You're getting the full power of Abacus in the cloud or on your desktop, whichever works best for the moment in time that you're in. So now what we're going to do is open up the simulation environment,
Mm-hmm.
and we want to create a mechanical scenario. So this opens up the desktop client. So although we're working on cloud data, we're going to be working locally to set this up, create a new simulation study, give it a unique name so we can refer to it later. And then the first thing that we've opened up here is the assistant. We've got lots of red circles, but this is a nice little guide to help us make sure that we tick all the boxes and get the right elements into our simulation. We could do all this manually, but the assistant just gives us those little nudges along the process to make sure that we assign all of the correct properties to this simulation. So like we say, we've got the simulation with assistant that we're going to be using for a lot of this, and then that helps us guide through. We've got some tie connections that we're going to use to connect the hub to the rubber bushing, and then also to the outer ring.
So nice little feature that.
It is a real,
Yeah.
and it just helps you tie it all together, so
Yeah.
it's regarded with just the one control node. So yeah, it really
So is
does.
that going to work as like one part then rather than assembly? Yeah.
Exactly. Yeah. So rather than thinking, oh, I've got three parts and they're just held together at points,
Yeah.
it effectively goes, well, this is just one thing. It's all glued together.
Yeah.
Like when I was talking to one of the other guys shortly, a little while ago, and they were mentioning that you could just model this as one solid object and then divide it up and say, well, this bit's made out of that material and that bit's made out of that material. But because we're in SolidWorks, we're modeling in an assembly way. We just use a coupling, a tie connection to effectively glue all of these permanently together with each other. And then we're
work
going
as
to,
rubber. Yeah.
yeah. So it's molded and everything's been compressed in. So, and then we're going to use a coupling connection the same way that we did with the resin in last, and where we say this is permanently bonded to something else, and this is how we're going to be able to get the forces in. So meshing wise, we've got a few new meshes compared to what we had in the resin. We were using the tetrahedral mesh last time. We've now got some hex mesh, and we've got some swept 3D meshes as well. A whole host of different meshes available in SIMULIA to be able to suit the construction of the parts that you've got. So in here we can see we've opened up the study that we started pulling together. We've added a lot of the points in the assistant. So we've got the setup, we've got the parts in, and we've got the connections. But now we're going to just have a look and see all the different types of meshing that we've got. In that central hub, we've used the tetrahedron mesh, and we can see there that we've got a whole host of various options that we can specify for it. For the rubber, for the outside, we've got the swept mesh. Again, really controllable. And then for the rubber, we've got another tetrahedron mesh. So, and then these are tied, like we were mentioning. So the rubber is tied to the outer ring. And then the rubber is also tied to the central hub. Effectively glue, designer's magic glue. They are one piece. And then we've got the coupling on the outside of the ring. So now we want to validate that manufacturing process. We want to put some materials on. So, click this. So we go down and select the materials library. SIMULIA has an extensive library of materials. We're going to search for steel. And apply it.
Mm-hmm.
And we're going to select which properties that we want to consider within this whole host of various properties that you can switch on and off. Obviously, some of them in this we're not interested in, but by selecting various parts, we can make sure that they're considered if they're affected in this simulation, they will be considered. So doing that again there. Now on the elastomer part, we've got a custom hyper elastic material model selected. Specifically, it's got an Ogden model to capture the strains and the thermal and thermal structural expansion properties. So it also combines with it any hyperelastic response. So we've really got quite specific with the materials that we're putting in there. Is that doing it again? It is, isn't it?
Yeah.
Need to figure out why it's doing that. So what have we just what's our next step? Now we need to consider that manufacturing process. So we're gonna start our simulation at the 430 degrees Kelvin, and we're going to start cooling that down to the 300. After that, we need to set up a process that puts that radial compression in, and then we need to release it, and we need to understand what all of that process has done, and that then gives us a good starting point to be able to work through on the rest of our performance simulations. So the next bit is setting that up. So we've created a simulation as our production process, and the initial temperature, as I mentioned, is 430 degrees Kelvin, and it's applied to all of the parts in the assembly, and that's our initial condition. The inner hub is clamped in place, and then a radial compression of 2 millimeters. We got to that bit yet? Cooling. So we've got the cooling. So now we're going to cool it down. Make sure we got all our outputs together. You see there, we've got just this one node, which helps us just be able to keep things simple. And we bring it down to 300 degrees Kelvin. So now that's our cooling phase done. Forming, we're going to apply that 2 millimeters radial compression. And then finally, we're going to release. So with the feature manager at the bottom here, we can see the various stages that are all going to happen and what parts of the assembly that they're going to happen to. So now we tell it that we're going to release that. So there we go. We've now created our initial manufacturing process of this bushing.
Mm-hmm.
Now, the beauty of creating this this first step as its own simulation is we've now can use that as a restart point within SIMULIA Abacus. If we want to run a whole host of tests, we've already talked about that we're going to run different forces on this. We don't want to have to run that manufacturing process simulation every time we want to do a test. So we're now going to say, please just regard that first part of the test as the same for everyone. Save the results that you get to the end of that one, and then the next tests that we're going to do, use that as the starting point rather than going all the way back to the beginning. So if we wanted to try
on that, Andy, then so you can make design changes, mods, do your tests, you know, get somewhere, get a result, test again. So you're almost doing a pause on the information, make the mod, then do a rebuild, yeah, and kind of press play, yeah.
Yeah. So yeah, almost another way of thinking about it is you walking down a road and you get to a fork in the road. What you're almost putting a peg in the fork of the road and saying, right, come back here. If that one doesn't work, come back to this point and go down a different one. So we're just able to understand that we know we're happy with up to there. Or another thing we could have done is looked at different compression rates on that that's out of casing to understand how much it actually pings back. Does it ping back 0.5 millimeter? Does it ping back yeah, so exactly that, Barry. Yeah.
Very powerful.
So in the performance test case, we're going to apply some various loads in the x-axis, 70 kilonewtons, y 35, and z another 70. And we want to sort of understand what that does, and then, just like we just mentioned there, why have we got the release step? Well, and that's because the linear behavior of the bushing, and we want to understand what effect that has on the final movement and the vibrations and the X, Y, and what have you. So now we're in the performance test scenarios. In the same way as we can see, I'm going to pause it just there because it doesn't stay on long. Well, no, it should be all right. In the same way as we could see what was going on with the production stage, we can now see that there's some 3 different tests that are being applied to this component. We can click through to them to start applying some of the properties to it. And you can see that we're going to apply force 1 and then release it. We're going to apply force 2 and release it. And then we're going to do force 3 and release that as well. So then we just need to set them up and say what they're going to be. So here we are, just also making sure that we've got some sensors in set up for all of these, so we've got something to be able to put into our output.
Mm-hmm.
Has it gone back to the beginning again? It has. Did we miss a step there? So how are we going to run these simulations? We're going to push them up to the cloud and run them on the 3D Experience platform. It reduces all the costs that we're going to have invested in a machine, just in case we wanted to run these simulations. We can buy credits and tokens as we need them, and it streamlines all of our processes. We've very quickly moved from having a CAD model in SOLIDWORKS to having a simulation based on that exact same CAD data in the cloud, ready to run. So the collaboration, that MODSIM philosophy, is by default starting to happen.
It's nice to not just think of the performance of the product, but actually the performance of the manufacturer of the product.
It is. As I say, it was a real revelation to me when I was talking to this guy, and he was like, "Well, have you actually considered the damage the manufacturing process is being put into a piece of steel when you bend it 90 degrees?" And I was like, "No, never thought about that." And he was like, "Well, of course, it's going to be different to what it was when it was just a piece of flat steel." And it was a real eye-opener to me that there's so much more to a product than just its finished product. Here we're sending this up to the cloud to do the simulation, and we're using 36 cores. It goes all the way up to 144. Will the 144 be quicker? Probably not on this one, because it's not the most complicated, and but we can give you some good advice on how many cores you're going to need for simulations as and when that comes across. We've got a whole team who are very clever with all of that kind of stuff. Now this is actually running in real time, so we'll skip forward a little bit, but the important part in this
Is the time it took there then?
Yeah, where is it? Wall clock time, 153 seconds. So
Yeah.
we're looking at 2 and a bit minutes it's taken to run all of that simulation for us. And the results are now ready. So the next stage, the physical prototyping validation. Looking at those results. So here we are. You can see that the hub is being put under tension, and then the compression is being applied to the outside of that ring, that 2 millimeter compression. So if we look here and here, we can see the deflection that's being exerted onto the rubber in there, and how it's going to be releasing the tension within that rubber. So we've got the von Mises maximum deflection. Was that? I think we clicked on set the range for our scale.
Yeah.
Now we can see how the pressures of there we go. The residual stresses inside that rubber bushing, being able to just focus down onto just the point that we want to look at. And we can interrogate this in a whole host of different ways. Looking at where those forces are. Again, section it through as and when we want to. And we can see this is all broken down into the steps. And we've broken it down pretty much into 0.1 of a second within that, and we can look at how things change transiently over time.
Mm-hmm.
So lots of different ways of looking at it there. So now we need to look at how it actually performs in the wild, or in a use case. So we've got the XYZ displacement, and we want to see how that is in effect working, and what the cumulative is with all of that as well. And the individual load cases, as we said, are going to be in 3 different directions, and we will get a different response in each of those. So we now run that test, and we've done it in exactly the same way as we did with the previous one on the cloud. It's a bad angle that we've chosen here, but you can see that the outer ring is moving longitudinally along the axes, and then it's moving away from us, and then it's moving vertically, and we can see that the rubber's also all going with it. So we've picked the highest force in the coaxial ways, maybe another way of saying it there, and you can see the deformation of the rubber. Now we're applying one of the perpendicular ones, and we can see where all those stresses are being developed. Again, lots of different ways of seeing exactly the same thing, and at different phases. But the effort that we'd have had to have gone into to be able to get to this point, if we weren't using simulation, we'd have had to tool up, we'd have to manufacture this, we might have had some shortcuts that we could go through, but still we're having to get all of this data in a very expensive way. So there we were just saying these are some points that we want to measure the force over displacement. And so we've got these 3 lines, one for X, one for Y, and one for Z. And that gives us something that we can start saying, well, actually, is there any improvements that we can make on this? If we go back to the design department and say, well, can we try this? Can we get a better performance for not much more strain? So that's exactly what we're going to do. I was playing the same thing again. So we're going to look at an alternative design. So in exactly the same way as we did with the resin, we're going to go back to SolidWorks, change that rubber bushing so that it's got a larger recess in it, so that in the left to right on my screen here, we've got less rubber, so it's probably going to be more flexible and allow more movement. So let's do that in SolidWorks. So with this one, rather than taking you through the whole process of of editing the sketch. We've modeled this other part, and we've got it as an alternative part, and we're going to go into the 3D experience, and we're going to replace by revision. So at the minute we're on A1, but we've modified this and we've got a B1. So we swap out that A1 for a B1.
Well,
so there
and
we go.
because you've got all the loads from previous, it'll fly through that, and in theory.
Well, so all that meshing and everything, yeah, it's all just going to go straight back in. It's all that we don't have to do any of that mechanical build study, and it's all just going to update and be ready to go. So now that's doing that. So again, this is the MODSIM loop that we were talking about. We update the simulation model and rerun the simulation and save a revised version. And we just go round and round, but all the way through the design process. As much as we want to test, we can. So now in the simulation world, we can see that we've got an update available to change the bushing to a B. So now we're going to just swap that out, exactly like Barry says. All of the setup work's been done for us because we did it in the previous simulation. So now it's just a matter of rerunning the test in exactly the same way, 36 cores again, and saved ourselves a host of time. No data format exchanges, no saving it as an intermediary file. We're literally working on the same data. Myself, and if I was Barry, me and Barry were working on this together, we could very quickly be iterating ideas and sharing them with each other to be able to see what we wanted to work with. And because everything in this is working and revision controlled, if we ended up with various different revisions, we could test the efficacy of mixing and matching different versions of things to try and get a really highly performant product. But so that's running, that's run, and now we've got a bunch of results back, and we want to figure out whether that revision and that idea of changing that rubber has been worthwhile. So we look in the results explorer. Now this allows us to open up multiple simulations and see them side by side, rotating the top one, rotate, so we're always looking at exactly the same view. So now if we go into section view, and we can see that the stresses in this, they've only changed very marginally, but then we can also see that the bushing is more flexible. It's giving that softer in this direction, especially. So we are improving performance for a very marginal increase in stresses, and this all fits within our KPIs. So we're ending up with a better ride quality for whatever's on the other end of this bushing. And you can see here, so the displacement of 17 point, oh, missed it, but the stresses and strains in that part are very similar, but the performance is better according to our KPIs. So we're happy with that change. We've managed to do a very quick iteration through of what works and what doesn't, and this is all learned knowledge that. Go on, Barry. Sorry.
Test it early, like your taste test.
Yeah, and because it's all just done, it's all set up in the same way as we did with the resin. It's there, or now we've set it up the once and we set it up early. It's very quick to just set this going again. So we've talked a lot about how we're using SolidWorks, and we're talking a lot about how we're using SIMULIA and the 3D experience cloud to be able to do that simulation. But the other part of the whole 3D experience is tying it all together and tying those departments together. And like Barry talks about an awful lot, it's that incentivization of co-design and co-simulate and collaborate. It's really it's the glue that keeps the MODSIM philosophy together, the actual communication of everybody who's involved in the process. So like we're talking about bouncing ideas off each other, especially in the modern world, people might not be in the office to sit down and go through things all the time. People might be working different hours. They might be in a different country. So by using the 3D experience platform, we can all interact with that same data. We can all comment on it. We can all interact and put our opinions down. And rather than this being lost in some email chain between me and Barry, or me and the design manager, or Barry and the QA manager, this all gets documented. And again, one of Barry's favorite things, the who, what, why, and when. And we can track and understand where all of these changes have come in. We can see that someone's asking, we need to remove this residual stress here. Other people can go in and look at all the models. They're not SolidWorks users, but they can even see the simulation results. They can start spinning this around with the simulation collaboration roles that are available.
Yeah.
Look at all the different states. So it's a word that I hear an awful lot, but the democratization of data and information. It wasn't long ago that all of this stuff would have just lived its life on the simulation engineer's computer, and he'd maybe have put out a PDF or a Word document report that gave the rest of the team information about performance at certain
Or it was a
points.
meeting, Andy. Everybody had to be in the one place, sitting around the boardroom, going through a PowerPoint slide deck. So it's now all live there at your fingertips.
Yeah, and oh, the pair of us are full of catchphrases, but could you just if my report only shows the state of that rubber bushing after the forming phase, what if you wanted to see it while it was just before that? In days gone by, you'd have come to me and said, oh, could you just do me a report at the cooling phase? Or right now, can you do it? Now all of that data is saved in the cloud. We can both get to it. You can get to it yourself. I can be getting on with what I want to be getting on with, and you can get that data, and we can, between us, be making some really powerful decisions about where we're going to go next, and based on real information rather than second-hand information or having to ask somebody else to create a report for you.
You've spent a lot of money.
Exactly.
Yeah.
Exactly. It just, the sooner we can make an educated decision, the better. And the better this product performs, the better our reputation becomes, which kind of conveniently wraps up the main bit of the seminar and brings us to the takeaways on it. So do you want to do these, Barry, or shall I? It's up to you.
Carry on. So good.
Yeah. So technically, we've got we've got a system that allows us to create some real simulation driven design decisions. You can see there that we were messing around, well, not messing around, but playing with different design concepts for the rubber within the bushing and seeing how that affected the performance of it without even having to cut a single bit of steel or an injection molding tool, and even considering the way that it was manufactured and what influence that would have on the study and the performance. From a business point of view, this just helps everything come together. It allows us to create more innovative products. Our designers are going to be less scared of coming up with something and putting it forward, because we're going to know whether it's going to work before we actually start manufacturing it. We're going to be able to find out whether it does work sooner, and we're going to be able to get it to market quicker than our competition. It's going to give us the reduced IT costs that we talked about earlier. All our data's in the cloud, the processing is done in the cloud. And with all of this comes the fact that our product is going to be more reliable, the warranty costs are going to go down, the recalls are going to go down, and we're just going to be seen as a better quality product in the market. Again, all of this allows us to stand up above and be noticed more than our competitors. This is the way that we are going to be able to get that market share, that extra bit that is going to make the difference. So there you go. So that's that's seminar 2 basically done. We've got 2 more to go. Oh, no, sorry, 1 more to go. Which will be on the 21st of June, which is next Tuesday. Registration is exactly the same as it was for today on the TECHNIA website, and it'd be good to see you there. Like we're going to be looking at the OMAX high pressure water cutter. Lots of very clever stuff going on with resonant frequencies and rigid and flexible bodies and how those harmonics are going to affect those. Really interesting. Again, using the same technologies and working in the MODSIM philosophy of collaborating between the 2 departments of simulation and design. So yeah, we look forward to seeing